But first, let's focus on those siliciclastic sedimentary rocks. Okay. These are the most abundant sedimentary rocks, which makes sense, right? Because remember, they are just formed from the weathered material of other rocks. They're formed from the detritus left over from the weathering of all other rocks being igneous, metamorphic, sedimentary. All other rocks can weather and then form into siliciclastic sedimentary rocks. And during transport of this detritus, especially by water, those mud-sized particles go into suspension and tend to be separated out from the larger sand-sized particles. Right? So the mud gets carried away in that suspended fraction. The sand, the gravel, it is left on the bed of the river. It's transported as bed load. So these sediment grains are separated based on their grain size. Okay? So the coarser particles get left behind. They go together, finer particles get carried away, they go together. And this separation leads to the division of siliciclastic sedimentary rocks into three main types. The ones that contain only the small fraction that got carried away, those are our mud rocks. The ones that contain mostly just sand, right? Those are our sandstones. And the ones that contain a little bit of everything before that material was actually separated based on grain size, that's our conglomerates. And this should all be a review for you, but let's just recap. We know that as this material is transported from source to sink, from mountains to ocean, by water, by wind, by gravity, its size is reduced because it's breaking and going through abrasion as it's rolling downhill. The finer the particle, the more easily it is moved by the wind or the water, so that those finer materials get carried even farther and farther away from the source. And along this pathway, not only does the sediment get smaller, it also gets more well-rounded and more well-sorted. Right, so once again, this is why you might find a conglomerate up near the source, but a sandstone or even a mudstone down by the ocean. All right, so let's talk about conglomerates. Conglomerates are a group that contain a few different types of rock, including conglomerate, which I know is confusing, but we're going to talk about two of the different types of conglomerates, one being conglomerate, one being breccia. Conglomerate is what we call a rock that has fairly rounded grains inside of it, whereas breccia is what we call a conglomerate that has angular grains inside of it. So conglomerates are typically formed in high energy environments, right, where you would get deposition of these large grains mixed in with small grains. So think like at the base of a mountain, maybe there was a landslide or something like that, bringing lots of different grain sizes down. The closer it is to the source, the angular it's going to be, you're going to get more likely to get breccia. The farther away from the source, not super far, but a little farther than where you get breccia, that's where you get those rounded stones, think like mountain streams, things like that, is where you're going to find that rounded conglomerate. Now, both conglomerates and breccia have materials in them, some of them being the larger material, think those gravels, those pebbles, that's what we call the clasts. And those pebbles and gravels are within a fine grained material, often like sand, silt, clay, that we call the matrix. So if a conglomerate or a breccia is clast supported, that means there's so many clasts, there's so many pebbles and gravels that they're actually touching each other and supporting each other. On the other hand, there might be fairly few clasts, and instead it's the matrix that is holding and supporting those clasts together. So matrix supported, meaning there's more fine-grained, clast supported, meaning there's more coarse-grained. And just like everything with sediment, this tells us how far away from the source is it, right? How much separation has there been already between the grain sizes? Now, because conglomerates and breccias are right, they have that matrix within them, that also means there's a lot of pore space within them. Right? There's a lot of little nooks and crannies in between those clasts. So the high porosity of these conglomerates can actually allow hydrothermal solutions, meaning really hot water that is carrying a lot of dissolved ions, to flow through them, pass through them. And we know that anytime you get too much ions in solution, that's hypersaturated, then those ions can precipitate out as a solid. And often when you look at a breccia or a conglomerate, you're actually going to find ores within it. This example has copper ore deposited within the matrix. So they can be pretty important ore resources. Talking about sandstones, we're moving from breccias and conglomerates to sandstones. These are the rocks that are made up of pretty much just sand. And we know that the most common sand in the world is quartz sand because quartz is really durable and sticks around for a long time. So as a reminder, sand is just a grain size class. So it's most often quartz, but it can be anything. Sand can be from any other mineral. It can even be from plastic, glass, things like that. It's just a grain size distinction. And the grain size is 0.0625 to 2 millimeters. Again, predominantly quartz, but could also include feldspars, shells, other rocks, things like that. Sandstones make up about 25% of all sedimentary rocks, and because of their resistance to weathering, they're commonly the most visible sedimentary rock, which is why in lab I bring up sandstone a lot. You have to be able to identify sandstone because it's everywhere. Sandstones form under all climatic conditions, which is also super important because it's very plentiful in the sediment record, and we can use them to identify climatic conditions, environments, things like that. And they have a worldwide distribution. So it's a really important resource to be able to understand in our sedimentary record. So sandstones can actually be pretty complicated. As I said, most sandstones are made up of quartz, but not all of them. And just like anything else, there can be a variety of different ingredients involved. So we're coming back to our tertiary diagrams. And you can see here on a tertiary diagram, we have the 3 ingredients: quartz, feldspar, and just other rock fragments. Know that these aren't the only ingredients possible. They're just very common ingredients. So if the sandstone is mostly quartz, we call that a quartz arenite. So that's more than 90% quartz. But if that sandstone starts to get more and more feldspar, more than 10% feldspar, we call that an arkosic arenite or an arkose sandstone. And we know that feldspar is a pink mineral, so it's going to make our sandstone have that pinky reddish color. On the other hand, if there are just other rock fragments in it, this can often cause the sandstone to be a dark shade, dark in color. We call that a lithic aranite or a lithic sandstone. By the way, aranite in Latin is sand. So the abundance of these 3 main types of detrital grains in sandstone depends on the composition of the rock in the source region that the sediment comes from, right? So obviously quartz and chert are the most durable minerals, so they are going to be the most abundant. But if the sandstone is fairly close to the source, you might get an arkosic sandstone. Now, sandstones that contain more than 50% mud, and again, mud is just a grain size classification. It's anything that's finer than sand, so 0.063 millimeters or smaller. If sandstones contain more than 50% mud in their matrix, then we call these sandstones wackies. In the past, you may have heard of the term gray wacky, same thing. These are typically dark colored sandstones. They're really easily mistaken for basalt because they're, black and kind of grainy, but they are wacky sandstones. And they're almost always of marine origin, and some of them even show that graded bedding that is formed during the deposition of the sand and other grains. All right, we've talked about conglomerates, we've talked about sandstones. Now we're going to go to the even finer grain size class, talk about the mud rocks or the mudstones. Mud, again, is just any grain finer than sand. That's less than 0.063 millimeters or 63 microns. And because it's very, very fine, it is transported very far away from the source, and it often only accumulates in very calm water, such as lakes, inland seas, the deep sea floor off the coast of passive margins, things like that. Mud rocks are siliciclastic, right? Not organic or chemical, they're siliciclastic, forming from mud, less than 0.063 millimeters in diameter, and most of the grains are coarser than 0.004. Or if most of the grains are coarser than 0.004, we call that a siltstone made out of silt. If it's even finer than that, we call that a claystone made out of clay. Mud rocks with a really high clay mineral content tend to split into really thin sheets parallel to the bedding. Just like in this picture, you can see those really, really thin laminations. We call this property fissility. It's often shows up in shales, this mud rock. And it's because the mud particles often are platey themselves. Once a grain gets that small into the clay region, it actually forms a little plate, a little flat, long grain, creating this fissility in mudstones and shales. Right. So mud rocks are of great economic importance, and that's because they're often the source of organic material for petroleum and natural gas, right? We said that mudstones often form on the ocean floor. We also know that oil and natural gas are made from those plankton that are in the ocean and settle to the ocean floor. So that's why you get shale. This marine shale is often a source rock. Um, uh, or they can also be a cap rock if there's material welling up from below them that cap these oil reserves. They can also be confined aquifers that are good for water resources. We'll talk more about oil and natural gas a little bit later if that didn't make sense to you. Now, the beds in mud rocks can vary from being massive, huge, to really finely layered, what we call laminated. And the facility shown in the shale in this figure A can be seen in the thin section B. Under a microscope, and they result from the clay-rich laminations alternating with laminations of richer detrital quartz grains, those larger quartz grains or carbonate grains. Right. So not all mud rocks are fissile, and many show no laminations at all. But it helps if they do. It's really easy to identify them if they do. And one of the reasons they can lose their layering, their facility, is because before the sediment is lithified into a solid rock, organisms can go in there and, like worms, like crabs, and mix up the sediment. We call that bioturbation. And bioturbation destroys any sort of layering or facility before it's preserved in the rock.